and we are the group 4. And today we'll discuss a topic that looks complicated at first, but it is actually very logical once you understand it. Implicit differentiation, along with its uses and logarithmic and inverse trigonometric function. I'm Clint, Ezra, Mananquil, together with my groupmates Gwyneth, Bentillo, Mary Joy Baldos, and Lourdes Solijon. Let's begin by understanding what implicit differentiation actually means. In most cases, when we take derivatives, we're used to equations like y is equal to x 2 plus 3x. Here, y is already alone and we call that explicit form. But sometimes y is tangled with x. They're both on the same side of the equation like x squared plus y squared is equals to 25. We can't isolate y easily. That's where implicit differentiation comes in. It lets us find dy over dx even when y isn't alone. The idea is, every time you differentiate a term that includes y, remember to multiply it by dy over dx because y is a function of x, even if it's not written as one.
Now, here's how we do it step-by-step method. First, differentiate both sides with respect to x. Second, multiply by dy over dx every time you differentiate y. Third, move all dy over dx terms to one side. Fourth, factor out dy over dx. And lastly, solve for dy over dx. Let's see how it works with a simple example. So, given x squared plus y squared equals 25, we differentiate both sides to get 2x squared, 2x plus 2y, dy over dx is equals to 0. So, solving for dy over dx, we get negative x over y. That means the slope of the circle at any point depends on both x and y.
Let's move on to logarithmic differentiation. This technique is super helpful when the equation is complex, especially when variables appear in exponents like y is equals to x to the power of x. Use when the function involves exponent, powers, or products. So example is y is equals to x to the power of x. Step 1, take the natural log in of both sides. So then next is differentiate both sides. So muna ni hitabo dy over dx is equals to mx plus 1. Then step 3 is multiply by y. So that gives us dy over dx is equals to y in x plus 1. Then last but not least is substitute back y is equals to x to the power of x. So that gives us dy is equals over dx is equals to x squared in x plus 1.
Now, let's apply implicit differentiation to inverse trigonometric functions. So implicit differentiation also helps in finding the derivatives of inverse trigonometric functions. For example, y equals sine to the power of negative 1 of x. So we can rewrite that as sine y equals x. Then we differentiate both sides, cos y dy over dx equals positive 1. Solving for dy over dx gives 1 over cos y. But since sin y equals x, we know cos y equals the square root of 1 equals x squared. So over dx equals 1 over square root of 1 negative x squared. Beside the solution, we have a summary table of inverse trigonometric functions under derivatives. So let's read it one by one. For sine inverse of x, write it as positive 1 over square root of 1 minus x squared. For cosine inverse of x, write it as the derivative is negative 1 over square root of 1 minus x squared. And for tangent inverse of x, writing as the derivative is positive 1 over 1 plus x squared. So these tables help us remember the common derivatives for inverse trigonometric functions, which are very useful when solving calculus problems involving implicit differentiation.
Let's try one last example together. So here, example 4, which is given x cubed plus y cubed equals 6xy. So given x cubed plus y cubed equals 6xy, we have to differentiate both sides. So we have here now 3x squared plus dy over dx is equals to xy plus 6x dy over dx. So this is why we get this, because we differentiated both sides.
So next is we group the terms with dy over dx. So 3y squared dy over dx minus 6x dy over dx is equal to 6y minus 3x squared.
And now, let's do the factor, which is dy over dx. So we have 3y squared minus 6x equals 6y minus 3x squared.
Now we have the final answer. Dy over dx is equal to 6y minus 3x squared over 3y squared minus 6x. Implicit differentiation is powerful. It works even when y isn't alone.
And to wrap up everything we discussed, implicit differentiation is used when y isn't isolated. You always multiply by dy over dx when differentiating y. It's useful for equations involving both x and y, or for logarithmic and inverse trigonometric functions. We hope this made the topic easier to understand. Remember, derivatives show how things change, and implicit differentiation just gives us another way to find those changes when equations get tricky. And this is Group 4, and thank you for listening.